Today on Xenolidon, we have in for repair a Lightspace Venus 22-watt laser. This is a very spicy laser, and not for good reasons. It has an overheating issue, so we're going to look at the three main causes for that. But before we do, we're going to go over some common sense safety issues when handling high wattage lasers. And that is, I recommend you get a fire extinguisher, as it's better than having your house on fire. For all other hazards concerning this, consult your local laser safety manual. Now, let's get this laser hooked up. One of the heaviest lasers that I've worked on this channel, but not the first time I've been inside of one of these. Alright, so the three main things we're going to look at. The first one, and the simplest one, is that the fans in the laser unit aren't working. The second thing we're going to look at is the thermal management portion of the system, and that includes making sure that everything is the right temperature and we don't have any problems with the NTC thermistors or the Peltier junctions that control the temperature of the laser heads. And then finally, we're going to make sure that the sensor for the actual case for the main heatsink is operating and able to turn on the fans. So it could be fans, sensors, or too much power being generated by a bad thermoelectric unit. So the three things we're going to check out. I'm going to be running this laser with Pangolin Quick Show through ILDA. So I'm going to go ahead and set that up, and we'll get into running the laser. Alright, I have everything set up. I'm going to power on the unit. Just a couple of things that I do to make sure that my eyes are safe. This one being a metal plate that is painted in black. Preferably you use a matte anodized surface. That way the paint doesn't get hot, melt. And it's reflected downward, so that way the specular reflection portions of the beam get diverted downwards on the desk, not outwards back at me. I'm going to start the laser at a low brightness, 25%. And I'm going to run one of the statics. I pick a circle, enable laser. Laser's on. And I'm going to bring up the brightness, set it to white, and see what gets warm. I grant you what you see on there is quite diminished from the full output of the laser. That's quite bright, so that gets rid of a lot of light and will provide for a much safer working environment. Now, while I do that and see what gets warm, I'm going to also take off the cover because we're going to check the temperature of the laser diode arrays that are mounted on the TECs on the inside of the case. We want to make sure that those aren't getting too hot or too cold. If they get too hot, they can damage the laser diodes. If they get too cold, they can draw moisture in from the atmosphere and dust and particulates. Gotta keep in mind that when that water condenses, even if it's just a little bit between the collimating lens and the laser diode, it has to shrink. That creates a vacuum. It condenses 1,700 times its original volume as a vapor. Something insane like that. But that's a negative vapor pressure in condensing objects. Alright, there's probably going to be an interlock, so once the case is open, the laser should shut off. And then we'll have to disable that interlock. Alright. Are you really compliant or not? Let's see if the laser shuts off. And it is. Oh, I haven't been in one of these units before. It's a slightly bigger brother of the other unit that I was in. Interesting. Alright, where's the interlock switch? There it is. Alright. I'm going to need to find something to defeat that real quick. We'll get back to the inside of the laser. Now that we have the laser open and running, let's take a good look on the inside of the laser and see what we have to work with and what the issues could possibly be. Line camera action away. Alright, here in the front of the laser we have the two laser beam steering galvanometers right here. I think they are the PT30s, along with the 2 galvanometer amps. We have this board right here. That's going to be the power supply driver for the laser heads. Over here we have the scan fail system for the laser, so this will shut down the laser if there's any problem with the beam steering galvanometers. That way people don't get blinded. And that also controls the invert functions on the galvanometer, as well as the interlock portion of the laser. Over here we have the DMX and ILDA daughter boards. And then the FB4. This is a Pangolin product. It's basically a built-in Ethernet controllable laser DAC instead of using the 25-pin ILDA standard. However, this one also does support the ILDA standard, which is what I'm using. Well, we have the 2 laser heads. This laser head right here, this is going to be a combination of the green and the blue. And this one is the red laser head alone. That's pretty cool to the touch. And oh yeah, that's making an NVIDIA product look cool. So far the fans haven't kicked on. So that brings us to a part of concern. So right here in the center, mounted down to the optical case, is going to be an NTC thermistor. You can check and see where that goes and whether it's good. And we can also check the laser head that has the green and blue lasers inside. Make sure that the thermoelectric cooler on the inside isn't failed and going into a thermal runaway condition. But my main concern right now is that the main cooling fans haven't kicked on. So I'm betting that's where the problem's going to be. We're going to go ahead and check the connectors on this board and see where that thermistor goes and make sure that those are seated properly. I've had problems with those real small connectors on the inside of these Lightspace lasers before. So we're going to go ahead and check out those things, run it for a while, see what happens. But yeah, it is definitely getting warm and those fans are not kicking in. Now for many of you, we're about to go into the climax of the video where I open up the laser heads. And what I'm going to be doing is checking to make sure that the thermoelectric coolers that are controlling the temperature of the optical train on the inside of the laser heads is working properly. So I have to do this because the outside temperature of the laser head doesn't tell us anything at all, because just because the outside is warm doesn't mean that the inside optical train is. So I'm going to open up the laser heads and we'll take a look, see what's going on. Laser's on. That's good. I'm going to start the laser, get it running. Before I do that, let's go and take a look at the inside of the optical assembly of the laser head. Now while I do this, I'm going to say, when you're opening up a laser head like this, you want to pull up as vertical as possible to make sure that you don't hit any of the delicate aligned optics on the inside. Carefully pull straight up as possible. Like that. Oh, beautiful. We're going to learn a lot about this laser. Actually, I'm going to disable it, and we'll go through the optics without worrying about damaging the cameras. No. Once again, as vertical as possible, just like that, and off. So this is the inside of the optical assembly. Much more complicated than what you initially saw. And each one of these will be cooled by thermoelectric junctions that are underneath the optical train. So this will have thermoelectric junctions under it. This one will also have thermoelectric junctions under it. And they're usually monitored by thermistors as well. Let's see if we can find those. This looks like it's a thermistor here, as well as this right here. And let's see. Right here. Okay. This looks to be the thermistor for the red laser assembly. So let's take a look at the optical arrangement, see what it looks like on the inside. Fine camera action once again away. The best kind of camera action for looking at something like this. Alright, so what do we got here? So this is the red laser array. It looks to have 32 individual laser diodes, probably the sharp 185 milliwatt 638 nanometer laser diodes. And let's go over what they do to mix 32 lasers into one beam. So this is what's called a knife edge array, and how this works is there's little reflectors, and you'll notice that there are rows of 6. So there's a row of 6, there's a row of 6, and this is a row of 6 right here, and those reflect the lasers as so. So laser comes out, reflects off this way, reflects off this way, reflects off this way, reflects off this way. You get a row of 6. Now you'll notice that the first row of 6 is lower than the middle row of 6, and the last row of 6 is higher. So that gives us 3 rows of 6. So lower row of 6, middle row of 6, and upper row of 6. That same assembly is on this side. So once again we have a row of 6, top, middle, and bottom. And then we have a couple of optics right down here. So what's going on down here is I got one row of lasers coming in, reflecting off this mirror into this optic. What is this optic here? It's a wave rotator plate, quarter wave rotator plate. All the lasers are mounted in as such, where the linear polarization, the electric field, is in the vertical, so it's going up and down. Same thing with this over here. So what this optic does is it changes the polarized component up and down, horizontal, side to side. That's important because of this optic right here. So any light that's in the vertical component will go through. That might not be right, actually, given how these work. It might be that they're all in the horizontal. Either way, it's important to note that this is a polarized beam splitting optic, or beam joining optic. So it's necessary for the polarization of one set to be vertical and one to be in the horizontal. So that way it can mix by the polarization optic right here. So changes horizontal to vertical, and it reflects both horizontal and vertical. Over here in the green blues, let's see what we have. Let's see this section right here. Probably going to be the blues. And we have another knife edge arrangement right here. And it looks like we have 2 upper and 2 lower over here. So 4 blues. What do we have over here? Obviously something is being joined with the polarization optics. So let's see. Alright, so these 2 little angled mirrors right here. Let's see if I can point to them. Right there. Those are reflecting this way, so these 2 are probably going to be blue. And same thing, we have a polarization optic right here that'll allow us to join those together. And we have an anamorphic prism pair. So what this does is it squeezes the form factor of those laser beams in one axis. In this case, it's going to be the horizontal axis, because that's the axis that the prisms are on. So let's see. Oh, well, there's green on those, so that's going to be the greens. And you can see that the greens are reflected off this way, giving us probably 2 rows of 2 here. So 4. Over here we have 4 more green lasers, it looks like, with another knife edge arrangement. 2 upper and 2 lower, giving us a profile of 4 laser beams here. 4 laser beams from here. Once again, we have a polarization optic right here, which will be this right here, and then we have the polarization pass and reflector, so wave rotator plate and polarized beam splitter, beam combiner, along with another set of anamorphic prisms for combining, for condensing the beam on the horizontal. So now, in order to make sure this is working properly, I'm going to turn up the lasers, let them run for a little bit, and I'm going to see if these remain cool, which they should. If one gets overly warm, so for example, this head, we had a very warm top cover. We want to see if the inside is getting warm or not, which is the important part. So, put the camera back up here. We'll go ahead and that's that. So, turn on the laser, we turn up the brightness. Let it run for a little bit. Oh, well, while we do that, let me point out what those beams look like on the inside. So that way you can get a really good idea of how they're joined. So over here on this optic, we can see those rows of 6 and columns of 3. Same thing over here, how they're joined. The wave rotator optic right there. The 4 green. 4 green over here. How they're joined. Get a beam profile of 4. Let's see if we can get a close-up on that. Yep, you can see there's 4 off there, 4 off there. And then we're going to go over to the blues, see what the blue looks like. Once again, looks like 4. I think it's more like 6. Boy, they cut it real close on that mirror, didn't they? Yep. Could have done better with that one. But yeah. Quite a beautiful optical assembly on the inside. And this is why they cost so much, is all those optics need to be aligned by hand. That's a very long and laborious process. But it makes these so wonderful to look at. That's beautiful. Absolutely beautiful. Alright, let's check those temperatures. Oh yeah, that's cool. That should all be the same temperature. That's about room temperature. Not a little cooler. And that's cooler still. So, the fact that these are cooler than ambient tells me that those thermoelectric units are working perfectly. So, the next situation that we should address is to figure out exactly what's going on with those fans and why they're not coming on, because it seems to be the only problem that I see. So, I'm going to put the laser head covers back on. We'll go in and investigate why the fans aren't turning on. Earlier in the video, I pointed out that there was a little thermistor down here, and that looks to be connected to a little board that has a MOSFET and a transistor. So I'm going to see if we can activate the fans manually by use of a potentiometer. So first thing I'm going to do is I'm going to open up the back of the laser, and I've already taken out most of the screws, and that'll give us a little bit more clearance inside of the laser to investigate what's going on. It looks like that little thermistor is held on, connected by a little connector, 2-pin connector. And I'll tell you, if it's because a little 2-pin connector failed, I'm gonna laugh. Alright, so it looks like we have power in, power out to fans, and then right here I see it. Okay, so power in, which will be these two, probably 24 volts. You can check that. And then these two, which should be going out to all the fans on the bottom. Underneath that, we have another connector where the thermistor goes to. I'm going to pull off this little daughter board with the fan controller on it, and we'll do some probing and some testing. Oh, stainless hardware. I wish you were magnetic. All right, pull that section out. Find something to lay it on, and we'll get to work on that. That'll do. Okay, so power up the laser. First thing to check is that I'm getting voltage going to that little daughter board. So plug the laser back in and test that voltage rail. I think we'll see 24 volts on that. So here's the meter. And what's all right, so let's see what the voltage is. $24 volts. That's fine. I'm gonna unplug the thermistor. Plug my little potentiometer thing in, and we'll get some information on that. Alright, if it's NTC, when the resistance is increased, the fans will go on. If it's BTC, when the resistance is decreased, if it's NTC, fan will go on. Let's test that. Fans have not turned on. Let's go the other way. Fans have not turned on. Alright, well. Let's see if there's power getting to the fans. Yeah. Awkward angle. No. Alright, so there's a problem with this little daughter board, it seems. Let's see. I'm going to pull this out. We can take a look at that daughter board and see what's on it. See what the problem is. Aha, I say. The problem has indeed been located. Let's take a look and see what that is. On this little daughter board, there's a little bit of burn mark right next to this little ceramic capacitor right there. So I think what ended up happening is when that capacitor blew up and shorted out, that took out the trace on the other side that goes to that diode right here. So I think I'm going to have to pull off the capacitor and run a wire to fix the trace. Maybe that'll fix it. I don't think any of the semiconductors are bad. So, see what we have to work with. First step, remove that capacitor. Alright, I'm going to go ahead and clean that up a little bit, put it in some alcohol, and we'll see what we end up with. Okay, I've cleaned off the board to the point where we can see what the problem is, and sure enough, that pad, when it blew up, burned away. We can clearly see that there's a break of the connection right here. So I'm going to have to run a bodge wire from this to this side of the diode. So let's go ahead and do that. That should repair the laser. So let's get started. Nope, that's not connected. Try again. Stupid lead pre-solder. I know, we're all thinking the same thing. Alright, so hopefully that's the repaired part. We can go ahead and put this back in the laser and see if it does its job. Oh, look what we have. We have fan spin. Nice laser. Good laser. Happy laser. Cool laser. Ready to go back to its home. Ready to be in use, in concerts, in different venues, making photons for everybody to enjoy, as a laser should. Nice, bright, happy, cool, coherent photons. Alright, let's get this laser put back together. Alright, it's time to take this retina removing rainbow machine out for a test spin around the block to see if it works. So, turn off the light. Alright, turn on the laser. Let's turn it up to 100%. Man, that's bright. Lightspace, you make some good stuff. Although, why no lasers? Okay, let's throw some fog in the air. That's a bright laser. I do not want to be in front of that beam. Nope. Oh, that's nice. Very nice. Now this laser is definitely efficient for converting electricity over to fun. Let's see if I can do some cool effects by slowing down the shutter on the camera real quick. Alright, here we go. Turning down the shutter. Yeah. That's the stuff. Doesn't wave. That's cool. Now that is just awesome. That is super awesome. Well, it looks good, so I think the laser is fully fixed. Remember, there's no Z in laser, but there's a Z in Xenodiladon. And as always, stay tuned for more.